motion, we can leave that for next week. And I'll start with relative velocity addition, which is one example of a two-dimensional kinematics. Then we'll go to projectile motion. So relative velocity addition. This is going to be kind of more of an application of what we learned last week too in chapter 3, where we added different things to each other. For example, we added displacements to each other or forces. And then one example of adding vectors was velocity. So this is going to be more focused on that. So velocity of A with respect to C, we can say it's velocity of A with respect to B plus velocity of B with respect to C. So these A, C, A, B, these are called reference frames. So reference frames. So the way you read this is velocity of A with respect to C is equal to velocity of A with respect to B plus velocity of B with respect to C. So these two reference frames are going to be the same, and you can kind of think of it as they cancel each other, and then A and C remain A and C. So easy illustration of this would be something like this. Let's say there's a belt like this in an airport. These belts are moving at, let's say, 2 meters per second. So this is the belt. And then you get on top of it with your luggage. And you start walking like this because you are late to your airline, right? Your airplane is leaving, so you're kind of sad that you're late, right? And then you start walking on the belt at 3 meters per second. So if I want to find your velocity with respect to the ground, how would I get that?
You add them up?
You basically add them up, right? So it's kind of logical. It's intuitive that velocities add up like vectors do, right? So the way we would say that is the velocity of the person with respect to the ground. So P is your A reference frame, so that's the person's reference frame, right? So P is the object, and G is the reference frame. So the velocity of the person, the object who is the person, with respect to the ground reference frame is equal to the velocity of the person with respect to the belt reference frame, right? So then that's, these second indices here are the reference frames, C, B, and C. They're reference frames, and then these first indices are the actual objects that are moving, right? So objects, and then these are reference frames. So person with respect to belt plus velocity of the belt. So now you're treating the belt as an object which is moving with respect to the ground reference frame, you see? And then the belt and the belt cancel out. So then the velocity of the person with respect to the ground, velocity of person with respect to belt is what? 3 I hat, because he's running to the right. And then the velocity of the belt with respect to the ground is 2 I hat, right? And then we can just add them and get 5 I hat meters per second. So I see velocities add up like that. So if this is 3 and this is 2, then it adds up. Well, what if you got on a belt that was going backwards? You're so nervous to get to the airline that you get on a belt which is coming toward you, and then you start running at 3 meters per second, right? And then you realize, oh no, I'm on the wrong belt, right? So then you have VPG, then this is going to be 3 I hat minus 2 I hat, right? I hat. So your velocity with respect to the ground is just going to be 1, right? Now, if you run at 2 meters per second, what's going to happen? Then it's just going to be 2 I hat minus 2 I hat, so 0. You're just basically standing in place, which is kind of what happens when you do the treadmill. You see, the belt is going backwards and you're running at the same speed so that you don't, you're basically standing in place. Which one is more effective in burning calories? Actually running 2 miles or standing in place and running with respect to the belt 2 miles? Do you run the same amount? Do you burn the same amount of calories? Huh? You're tired less when you're doing like this? It's weird. I mean, people sometimes say actual running is more effective.
It's because technically you're not actually running. You can lift your foot and the belt's moving. So it's doing a lot of the work versus you had to push off of your legs to move forward on the ground.
Yeah. There's probably some mechanical dynamics happening to the bones and stuff. In terms of physics-wise, you're still doing the same amount of work because the belt is going back and you have to do work to just stay in place, you know. But the mechanics of how you jump, maybe you jump more vertical.
Because when you lift your foot up, your other leg is pulled back.
Yeah.
Instead of having to push forward.
Yeah, exactly.
I had to study that.
Oh yeah, you had to?
Yeah, I was studying
kinesiology. That's kinesiology, physics of sports medicine and all that. And of course, there could be all kinds of varieties of this. You could have the belt is going this way, then you could be running this way across the belt at 2 meters per second, right? And then that way you're going to end up going this way, right? So if it's perpendicular to each other, right? So if the belt is going this way and you're running across the belt, then you end up going 2 rad 2 at an angle of 45. You see? So then you end up going at an angle. Or you could have some kind of weird angle, 30 degrees, 40 degrees, so you can add them however you like. So basically that's how the velocity vectors are going to add up. Of course, we're assuming our velocities are much less than the speed of light. If you were to do relativistic velocity addition, right, then you have to change this formula and write it like this. One plus VPG, VPB, VBG over the speed of light squared. That's called relativistic velocity addition. Relativistic velocity addition. Right, so if there's a rocket going at 0.8 the speed of light, and I throw a baseball at 0.6 the speed of light, what's the speed of the baseball with respect to someone on the ground? Right? I'm really strong. I can throw a baseball at 0.6 the speed of light. Okay. So, well, Kiledjian addition, like if you ignore this, right, it would say, 0.8 plus 0.6, 1.4. And that's where Einstein steps in and says, no, nothing can even appear to go faster than the speed of light. So you can't do 1.4. So you have to do this equation, 0.8 the speed of light plus 0.6 the speed of light over 1 plus 0.8 speed of light times 0.6 speed of light over speed of light squared. See? So then you're going to get 1.4 speed of light over 1 plus speed of light squared is going to cancel, right? So if you're 0.8 times 0.6 speed of light squared over speed of light squared cancels, you get what? 1.48. 1.4 speed of light over 1.48 the speed of light. And now the universe is happy. Nothing can even appear to go faster than the speed of light. So then you have 0.9 something 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 speed of light. See? So that means if I shine a light beam here, going at the speed of light, someone is looking here, the baseball will fall behind the light beam. Even though the baseball is going 0.6 the speed of light, and it's riding on a rocket that's going 0.8 the speed of light, the baseball says, oh, I can finally beat the light beam. The light beam is always going to win, right? So there's almost like a barrier when you reach the speed of light, like almost like a shield that shields it from going faster than the light beam. So this guy is going to always be ahead. Then the baseball is going to be like this. Now, if you put regular speeds here, like 80 miles an hour, 60 miles an hour, right? 80 miles per hour plus 60 miles per hour over 1 plus 80 miles per hour times 60 miles per hour over speed of light is how many miles per hour? 186,000 miles per hour. No, it's actually 186,000 miles per second. Miles per second. Now square that. Well, what's going to happen is that I have to first convert this to miles per hour, then I have to square that. This over this is going to be 0. Right? So 1 plus 0 is just 1. And then you're going to get 140 miles per hour. See? So what ends up happening is for speeds that are regular speeds on Earth, these two, the product of these two is negligible compared to the speed of light squared. And then the relativity is not noticeable on Earth, right? So relativity is not noticeable for things that are going slow. Quantum mechanics is not noticeable in the world of the macroscopic, right? It's only noticeable in microscopic objects. So that's why we don't feel quantum mechanics and relativity in our daily lives. Okay, so now let's do a vector addition example, specifically having to do with velocity addition. An airplane leaves Miami, Florida, heading for Seattle, which is 2,400 miles away at an angle of 38 degrees north of west from Miami. So an airplane leaves Miami, Florida, heading for Seattle, which is 2,400 miles away, at 38 degrees north of west. And assume there's a constant wind pushing on the airplane at a speed of 80 miles an hour at 18 degrees east of north. If the plane wants to get to Seattle in 4 hours, what should the airspeed and direction of the plane be? So in other words, if you already know that there's that wind pushing you, how should you correct your position and your direction? How should you go? How fast should you also go so that you end up going there in 4 hours? So this is an example of velocity condition, right? So you are here. This is Miami. And let's say Seattle is here. So you want your velocity of the plane with respect to the ground to be from Miami to Seattle, because when you land, you want to end up in Seattle. So that's velocity of the plane with respect to the ground, right? So VPG, velocity of the plane with respect to the wind, we don't know what it is. Plus the velocity of the wind with respect to the ground. You see, the wind is the reference frame here, and then here it's the object, like the belt was, right? This is the velocity of the plane with respect to the ground. So in this example, which one am I trying to solve for? Let's see here. Well, we know that you want to go a distance of 2,400 miles is the distance, and you want to make it there in 4 hours, right? So 600 miles an hour. So your effective speed with respect to the ground reference frame, because you're going to cover a distance of 2,400 miles, right? So your effective speed with respect to the ground is 600 miles an hour. So that is the magnitude of the VPG, the plane's velocity with respect to the ground. That's 600 miles per hour, right? Then what? The direction of that vector is what? That's the direction from Miami to Seattle, 38 degrees. North of west. So that means we know this vector, VPG. So we're trying to find this one. VPW so we're trying to take this and subtract. So this is more an example of vector subtraction then, right? So we're trying to find VPW. So then what? Then we're going to break this up into components. VPWX is VPGX minus VWGX. And then VPGY minus VWGY is VPWY. Today's by the way, the extra credit lecture. So after this, go eat good dinner, and we go to Pasadena, Caltech, Kip Thorne, right? Black holes. So remember, the auditorium holds 700 people, but there's probably going to be 1,700 people there waiting to hear the lecture. No, I don't know. But let's all try to get there early, see if we can get good seats. So now we should draw and visualize what this vector looks like. VWG, what's the velocity of the wind with respect to the ground? So now that one is 80 miles an hour, 18 degrees east of north. So of course it's shorter than this. VWG, so this angle is 18 degrees, right? So essentially, we're taking this vector, VPG, and we're subtracting VWG. We're subtracting this. So how do you subtract them visually? You switch this, right? Minus VWG. Then you put that to the tip of that. Then that's the vector difference of the two, which is VAW. So essentially the airplane should head a little bit south of the Seattle so that the wind can push it up, right? So you're heading this way, but all along the wind is pushing you so that you end up there correctly. So now we're going to do the APG has a magnitude of 600 times cosine of what? Now we get the true angle, right? If this is 38, this angle is 180 minus 38 is what? 142? Yeah, 142, right? So then you get cosine of 142 minus dWg, which is 80 miles an hour, times cosine of what? Then we take this angle here, which is what? 90 minus 18, so 72, right? So remember, we always work with the actual angles as measured from the positive x-axis. So 600 cos 142 minus 80 cos cosine of 72. And that one will give you VPWX. Okay? Yes.
Sorry, I don't know.
PG is rated PG, like the movies, parental guidance. No. The velocity of the plane with respect to the ground. And then velocity of plane with respect to the wind. Right? I'm not gonna see PG the regular way anymore. Rated PG. Plane with respect to ground. Right? Okay, minus 80 times minus 497.528 miles per hour. And then VPGY is going to be what? 600 sine of 142 minus 80 sine of 72. Okay, so then what's going to happen? Oh, okay, so what does the problem want us to do? What should the airspeed of the plane be? So how fast should the plane be going in the air? Well, what is that? That's the magnitude of this vector. That's what the speedometer on the plane should be showing on the average. You take this squared plus this squared and then square root it, right? So VPW square root of 577. So does that make sense? He should only go at 577 miles per hour, even though people on Earth are gonna say, no, you were going at an average speed of 600 miles an hour because you traveled 2,400 miles in 4 hours, you see?
when you land, what are people going to think? Your average speed was 600, right? Because you covered the distance of 2,400 in 4 hours. But you tell them, no, I was actually traveling at 577. So was the wind helping you out or hurting you more? Yeah, in this case, it's helping you more than hurting you. If the wind direction was more like this, less than 45 degrees, would it be hurting you or helping you more? Then it's hurting more, right? Because it's more to the right. Because you're trying to get to the, you're trying to go to the left, right? So if the wind speed is more this direction, it's pushing you to the right. But it's also pushing you up, but it's pushing you right more than up. But because it was only 18 degrees, it was pushing you up a lot, but pushing you right less. So it was hurting you and helping you, but it was helping more than hurting.
Yeah, the reason why is because they two vectors, degrees of two vectors is less than 90 degrees. That's why it's kind of like there is like the push on your direction.
Yes, it's helping you more than hurting. It's pushing you.
Yeah.
So you're saying if the angle between these
Yeah.
was
Like V
more than 90, you're saying?
less.
Or if it's less than 90, it helps you more.
Yeah.
Oh, okay. Yes, yeah. You're right. Makes sense. Okay, let's see. Oh, and then the angle, what should the direction of the plane be? So even though you're going 38 degrees, this direction here is going to be less than 38, right? So how do we find that? Well, tan inverse of that over that, right? Tangent inverse. Now I don't need to put the negative because once I get the angle, then I'm gonna write down whether it's north of west or north of east. I'm gonna describe it that way. .52 degrees north of west, right?
It's tangent inverse of that whole
Yeah.
thing, right?
Yeah.
And can you explain why you don't have to put the negative again?
Well, because if I put the negative, it's just going to give me this angle, negative 30. So my goal is just to get an answer and then express it in terms of west-east direction. To me, I don't really care whether I get a negative 30 or a positive 30.
Oh.
Because my final answer is going to be north of west.
Oh, we're just
or-
trying to find that angle.
Yeah, I'm trying to just find that angle, the
Oh, I already know
magnitude
it's
of
right
that
at
angle.
right?
Yeah. So I'm trying to. This 38 degrees was this one. From here to here was 38, but this angle is 30.5. So even though people on Earth are gonna say, "Oh no, you went the direction of 38," but you're gonna say, "No, my compass was showing 30. I didn't have to go at 38. Actually, you should go at 38, right?" Okay, how about if we slightly change this problem and say, how about if the wind started not exactly when you started the flight, but it started after 2 hours after. So you were already 2 hours into it, and it was calm weather, and then all of a sudden this wind starts pushing you. Now how should you adjust yourself?
Just change your starting point.
Okay, so how do we account for that? I could do this anything, 1 hour, 3 hours, 2 hours, right? So then that means if you were going to Seattle and there was no wind, that means you were actually headed this way, right?
38 degrees, right?
Yeah, at 38 degrees, and you were already halfway there because it's 2 hours, right? So the picture changes. So maybe something. Well, what does the new picture look like? So like you're going like this. So now you're already here. So it's almost like putting a new XY axis there, right? And so now this is Miami. Now this is Seattle. And so now, so it's almost kind of like this, like that. So from that point on, you say, "Oh no, there's a wind pushing me up, so I should go slightly to the below it, right?" But how do the numbers change? The direction of the wind is still the same. The speed is still the same. In other words, what has changed?
Just like 2 hours.
VPG, this is VPG, this is VPW, this is VWG. So we have VPWX. So in other words, I'm going to use the same equation, and then figure out what's changing here, right? VPGX, is that changing? In other words, I have half the distance to go now, and half the time left. No, it's still the same, isn't it?
Yeah. It should be the same equations in angle.
So has anything changed?
Just the velocity, G velocity has changed because there's wind after 2 hours. So from
Well, how is the equation going to know if anything has changed? If you put here 600 cosine of
the same angle.
that same angle, right?
Two different.
Can't you find it?
142.
Huh?
Can't you find it in terms of displacement and divide by time?
Yeah. But haven't you gone half the distance already?
Yeah, so you just do half the displacement.
Yeah.
320, 160 displacement.
Maybe the first display, second part, and then add them at the end.
So is the 600 changed?
Last year,
Yeah,
originally it was 80 miles per hour going 4 hours. A total of displacement might have been 320 in that direction.
Oh
But now
no,
you
I
have-
never did the displacement of the wind. I just did 80 miles an hour. Well, you're saying do the displacement of the wind?
Yeah, that's what I did.
Or you did it in terms of distances?
And then after that, divide by time interval. Because the airplane took that long.
Okay. So he's saying do in terms of displacements. So if the velocity of the wind is 80, now you multiply by 2. Whereas over there you multiply
By 4.
by 4. Oh, he's saying treat this like a displacement problem rather than a velocity.
And then divide by the whole time now.
Then divide by time
By
afterwards.
velocity.
And maybe we have to do it that way because in terms of velocities, it seems like nothing changes. You see what I mean?
Breaking small.
In other words, the problem, there's no way for the mathematics of the problem to know, oh, now the wind started 2 hours later. The velocities aren't going to know that, but the displacements are, right? So he's saying treat this like a displacement of the plane with respect to the wind, displacement of the plane with respect to the ground. Smart dude, right there in the corner. Always be careful for the corner, guys. Okay. Right? See what I mean? Instead of velocity. So then he's going to say displacement of the plane with respect to the wind in the x direction, displacement of the plane with respect to the ground in the x direction. Well, what's that displacement? This is 200, how many miles are left? He's got 1,200 miles that are left, right? Right, so he's going to say 1,200 cosine of 142 minus, because that's how much left is displacement is left from here to here, right?
But isn't it supposed to be 20? Because that's the total displacement. So like whatever displacement caused by the airplane plus the displacement caused.
No,
by
we have to subtract. It still is a vector subtraction problem.
Yeah.
And now what's this displacement? It's going to be the velocity of the wind, how long the velocity of the wind has lasted, right? So 80 miles an hour for 2 hours, right? So what's that? So this displacement becomes 160 miles. Is that what you mean?
For the
Multiply
left.
80 by 2.
Yeah, for the left, but I still think the effect on the right should be 24.
This thing is 2400.
Because it should be that should be the total displacement, right?
No, because you've gone halfway already.
Yeah.
But then if you treat it like the whole thing, it's like the plane should travel this way in 4 hours, and then the wind in 2 hours, basically that way. But overall in 4 hours, the plane should travel from the Atlantic Ocean. Yeah.
You would draw one vector instead of like two pieces like
Let's see if we get the same answer.
Okay.
I don't think something seems fishy about that. 1200 cosine, and then wind is going to be 160 cosine of 72, right?
Is it 2 hours after your flight, the wind started? Or it first starts, and then when you take off? After?
And then you're going to do the total displacement. So that means the total displacement of the plane from that point from here to here has to be 1155.104. Then you divide that by the time remaining. So the velocity of the plane with respect to the wind is the displacement of the plane. This is VPW. Displacement of the plane with respect to the wind divided by the time remaining, which is going to be 1155.104 over 2.
It's like the same answer. 577.
It's the same answer as that?
Yeah, it's the same answer.
As the first part?
Yeah, it's the same answer. Like it didn't change it.
Huh?
The velocity, yeah, that's the same.
It should be the same, like no matter what. Because like this wind just starts like after 2 hours into the flight. It doesn't really change anything. Like, because the direction of the wind is the same, and then the velocity, like the initial velocity, is the same. So
The
it doesn't
answer I
really.
got after considering it was 24 I got only 10 miles per hour faster.
Doesn't the direction of just the direction of the plane?
How about the direction? Does that also come out the same? This divided by that?
It should be the same.
You wouldn't have to adjust the direction after the wind begins to blow.
You pretty much just multiply by 2 and it's the same as. Didn't you see that? Like, go back to the displacement.
It'd be like 4 degrees more north.
What is this?
No, I didn't mind.
It's the same.
It's the same?
It should be the same. Trust me, you just multiply.
It's like, don't worry, it's gonna be the same. Don't even do it. It's gonna be the same.
Because you just pretty much you just multiply by 2. Look at the equations right there. dp wx d, d something like y. You just multiply by 2. 600 times cosine. 1,200 times cosine. 160.
Why are you using
It is
all
the
like
same.
instead
Yeah,
of,
it should be the same.
2400 for the.
Because you're halfway there already.
What if you consider like the whole time the airplane is in motion as one vector, and then the whole displacement of the wind as another vector, and the final vector should be 24. Can you do it that way? Instead of breaking up the velocity of the airplane.
But didn't the wind start sometime later?
Yeah, but I'm just considering like the velocity of the airplane as one vector.
Oh, but now it's a smaller vector.
But the velocity of the plane by itself without wind should be this vector, and then given that the wind happened for 2 hours at this speed, then with that displacement added overall, it should end up being.
Ah. Is this giving us the same exact angle too?
Yeah.
Okay, then how I'm doing it is wrong. Can't be the same. Because it should change
The vector
whether
should
the
change
wind
when the
started
wind
right
starts.
away or
Right.
not. It can't be the same. Can't be. There's no way. Has to be different. How much you count for the wind depends how the duration, how long the wind has existed. Can't be that it's irrelevant. So then you got to go back and say, assume that you're just starting and you have a distance of 2,400 miles to go. And now there's a vector that is 160 miles. Right? Is that what you're doing? Because when you did it originally, what'd you do? You
I just
assumed
made
that
it
the wind
360
was for 4 hours,
Yeah, so it's 3.
so it'd be 320.
Yeah, that's all I did.
Okay, so now you're saying do 160, but keep this as 2,400. So you're right? Or is it just right because it seems to give you a different answer? Let's try to understand why his logic works, not just because, oh yeah, it works, it gives you a different answer.
Because the displacement of the airplane relative to the ground plus the displacement by the wind should be what overall what you see.
So you're saying the distance that the plane has gone, you shouldn't worry about that.
Yeah. You just average it into the total velocity. It's because if you had an airplane that started from origin and moved that way for 4 hours, and there was a wind for 2 hours going in that direction, overall you would end up with getting to Seattle at 24.
Yeah, okay. So now, does that change the answer? 2,400. So now this becomes 2400. And then this becomes 2400. I'm sure that's going to change the answer, right? Because these numbers are going to change. These numbers are going to change. Then I'm going to divide it by 4, right? Instead of 2. So this changes, and then this changes. So tell me what you get for this.
It's like 587.5.
Oh, this one. It should be bigger than this.
Times by 4, so.
I'm kind of confused right now. Like, the wind starts like after 2 hours.
2350
Yeah.
point something something.
No.
Then it takes
starts after
2350
2 hours, not like
Divided by 4.
divided by, this time he does it by 4. Right?
Yeah.
Then it's gonna get what, 587?
Yes.
Point
542.
542. So that means he has to go faster now? He has to go closer to the 600 now. Right? Or because the wind has been helping him for less amount of time. You see? Remember when the wind was helping him all along? He only had to go at 577. Now he goes without the wind. Now the wind comes up and he says, oh yeah, great, the wind is helping me. But it's only helping you for 2 hours. So you can drop your speed, but not that much. That makes sense. In other words, if he had gotten an answer here that was less than 577, I would say, no, it doesn't make sense. It should be more than 577. Yeah. How about the angle then? Then you do the angle, it should be this, whatever you got here, divided by whatever you got here, divided by whatever you got there. And I believe it should be larger than 30, closer to 38. North of west. So now you know how to handle those?
The total displacement, so they just considered it as a whole, the whole trip from the very beginning, rather than putting it in that. So they changed the total displacement here.
Okay, now you do yourself. What if the wind came up 1 hour later? Okay, and then now calculate how fast you should go in the direction. 1 hour later, and then you have 3 hours. 3 hours of wind.
Essentially, this is where the normal vector would have been.
Wait,
right?
there's 3
And at
hours
that
of
point
wind?
it turns.
3 hours of wind, yeah.
So at that midpoint, we compensate for the wind, right? So instead of being a straight vector, there's like 2 vectors, this one and this one, right? And then
Yeah.
we create a new vector here, and wouldn't that be what we're looking for?
He's saying don't do that. He's saying imagine from the original, not from where you
Oh, no,
are.
I'm still saying the original. I'm saying-
Yeah.
So this is where the second vector would be,
I can-
right? And then from this point, the original point to this new point is one new vector. And that would be what we're looking for, right?
Yeah.
Okay.
Yeah, so now do it if the wind started 1 hour later. Try not to look at the board. You do it it's fresh.
you mean like 1 hour after you take
1
off?
hour after you take off, yeah.
wind start and 1 hour after takeoff.
So your airspeed is going to be between 577 and 587, right? Your final answer. It's 1 hour after takeoff, the wind starts.
Before the point we discussed it was 2 hours. Or less.
Yeah, the other one was halfway through your trip. The wind starts. It's tricky, kind of, huh?
Yeah.
But remember, instead of velocities, try to think of it like he's saying about displacements. Then afterwards convert to velocity for this one.
Just the amount of time.
The amount of time that the wind has lasted, treat that as a displacement.
Yeah, but the amount of time you travel in 1 hour depends on the second part of the process.
Don't even worry about that, right? Don't even worry about how long you've traveled for an hour. Well, the speed was going to be 600 because he's assuming he's going at constant speed and he's aiming for that. But it still didn't work. I did the 600, then added the house equation.
time when it's on the path, and then that's that. That's like the split, that's like, and that's like the final path. And it's all on good.
I thought I did do that, but it's not good. I did it all on good.
I feel like I kind of like know the reason why the way you did like didn't work because it's in two different planes. You see that you said like two different planes, and the one you use like 1200 times cosine is in the left plane, but the reference plane should be the right one. That's why you're gonna plus some coordinates in the right planes to make it
Make it equivalent planes.
That's right. Do you know what I mean? Because they take like two different planes.
But then can't you make it a smaller displacement? So like after that first completed, it needs to do 1200 in this speed, and then you add this, you find the displacement of the aircraft, and then add that to the displacement of the wind, so it's finalized of that, and divide the whole thing by 2 to find the velocity.
It could probably, but you know what? Since your method worked, I think your method is easy. Just consider the
The
wind as
displacement
lasting
doesn't
for
change.
the
Yeah, the displacement doesn't change.
I think his
That's-
method is quicker, and you don't need to worry about where the plane is when it starts.
Yes, you're right. If you were to use your method to do it, you're gonna plus the coordinate, which is 600 times the cosine. That cosine 38, the initial velocity. Because you have two planes, you're gonna add them up, and that's gonna be the final answer. You can still do it that way. It works.
Yeah, it's almost like you're almost doing the vector sum of 3 vectors. You're doing this,
Yes.
then you're going this way, then the wind is pushing you.
That's right.
That's right.
It's almost like the vector sum of 3 vectors if you do it my way,
Yes.
right?
I mean, it's possible if you find a displacement of the last 2 and then divide by the time it takes, but
Yeah.
if you want, you can consider the flight of the airplane as just one. If it's the same.
Yeah. So anyone, you guys got it? What's the airspeed? It's gonna be between 577 and 587.
582.
Oh yeah, right, somewhere in between, right? Something, something. And in the direction between 30 to 38, 32.5. Nice. Huh? Yeah, then just divide the displacement by 4 hours.
Find the displacement of the airplane.
Okay, so practice that. See if you get that answer later on. Practice that. If you maybe in the SI session. Okay, now let's do projectile motion.
The first hour of the flight is dependent on the last time.
We're just thinking about
the last 3/4.
Cool, huh? When is the next SI? Friday? So Friday you'll work on that? No, this don't work on that because this is not on this test, right? I mean, it can be on the Monday's test because it's just vectors, but it's not going to be. Monday, yeah. Remember, we'll start 1:45 sharp, and then we'll go to 3:30, hour and 45 minutes. Okay, now let's do projectile motion. So projectile motion is a more general version of threefold motion, where we were throwing something up or we were throwing it down. So we have a person launching a projectile with a certain initial velocity. So the first thing to do is always break up the initial velocity into two components. The x component of the initial velocity and the y component of the initial velocity. And then you treat the x component separately and the y component separately. In the x direction, since there's no gravity operating, we have the Vx will always equal V initial x, which is going to be V initial cosine theta. So in the x direction, we're going to assume that air friction is negligible, right? So if air friction is negligible, then the initial velocity of the x direction always stays the same, and it's equal to the initial velocity you throw it at times the cosine of the angle. And the direction that it travels in the x direction, as you launch the projectile, the distance that it travels in the x direction is equal to what? Well, since there's no acceleration in the x direction, it's just equal to vxt. And you don't have to do half at squared. So x is equal to vxt, and then vx is equal to v initial cos theta. Now in the y direction, you got the same equations that you have in free fall, right? What's going to happen to the velocity as you go up? The x direction velocity is going to stay the same. The y component of the velocity is going to start reducing. When you get to the top, the x direction of the velocity is still going to the right, but the y direction of the velocity reaches 0. Vy is 0. Right? And then after that, when you start going down, Vy gets negative, right? Vx, Vy. So Vy gets negative. When you come back to the same height that you throw it from, what's going to happen? Vx, Vy, V final. Well, if you ignore the effects of air friction, when it reaches the same height, it should be going just as fast, right? Because it's going to have the same kinetic energy that you threw it from. The V final y should be equal to the negative of the V initial y. This is V initial y. This is V final y is negative V initial y. And the angle should also be equal to the initial angle but negative of it. So the theta final is equal to negative theta initial. So if you throw it at a 50-degree angle, then this is going to be negative 50, which means it's going down. See? After that, what starts happening, if you allow it to go down more, the velocity in the x direction stays the same, but the velocity in the y direction gets bigger and more negative, right? So now, the total velocity starts increasing. And then what happens to this angle? It gets more and more what? Steeper and more negative, right? So if it's negative 50 here, right? If you threw it at 50, here the angle is going to be 30. Eventually 20, 10, 0 degrees, right? Then negative 10, negative 20, negative 30, negative 40, negative 50, and then here maybe negative 70. And then the more steeper it gets, it's going to get more and more negative, right? So what are the equations of the y direction? So we have V initial y is equal to V initial sine theta, right? V initial y is V initial sine theta, and then y final, then you have the equations of the free fall, right? Remember you had 4 equations, equation 1, equation 2, V final y is equal to V initial y minus 9.8 t. So these are the same equations that you have for test 1. Except for test 1, we don't put the subscript y. We just say V final is V initial minus 9.8, because in test 1, you're assuming that somebody is on top of a building or something and it's throwing the ball up or down, right? So you don't have to put the subscript y. But here, if you're throwing it at an angle, then we say V final y is V initial y. And then how about V final x? Well, Vx never changes. It stays the same. See? So then you have here y final is y initial plus V initial y minus 4.9 t squared. But of course, if you're in the British units, you're going to use 32 up here, right? And then what are you going to use down here? 16, right? It's half of 32. And then the third equation, so this is twice acceleration, 2a. This is twice 32. This is half of 32, half of 9.8. And then the last equation, what's going to happen? Y final equals Y initial plus what? V initial Y plus V final Y over 2t. Okay? A lot of the applications that we do for projectile motion are sports related, but they don't always have to be, you know. But it just kind of makes it fun when we do a lot of sports related problems. Or you could do airplane, you could do tennis, basketball, baseball, anything having to do with projectile launching. So let's see some problem like this, let's say. So maybe you guys are hired one day to be the shooting coach, right? For a basketball team. Then you take your TI there, you know, whiteboard. It's all about analytics these days, right? Math, analytics, numbers, statistics, everything. Sports talk is all about analytics. Well, bring some physics into it, right? So he goes, I prefer shooting at 28. So 6'6". So then, what do we know? How far away is the free throw line from the basket? Huh? 15 feet? So that means he's like right here. And then the basket is 10 feet high, right? Something like that. So his initial angle is 28. And V initial we don't know. The distance from here to here is saying is 15 feet, and then the basket is 10 feet high. And then he's shooting it from a height of what? Initial height is 6 foot 6 inches, which is 6.5 feet. You can use here 6.6, you know, because remember 6 inches is half of a foot, so you have to change it to a decimal. So then what are the equations here? We have V initial x is V initial cosine 28. V initial y is V initial sine 28. V initial x is V initial cos 28. V initial y is V initial sine 28. And then we have x equals to Vxt. Right? Remember, there's no acceleration in the x direction. Vx is equal to what? V initial x. So Vx never changes. So then x is equal to Vx, which is V initial cos 28 t. And then x is equal to 15 feet. So there's two unknowns there. We don't know the V initial that you're throwing at, and we don't know the time that it takes to get there. Okay, now what's V initial y? Oh, we already said that, right? What equation should I use in the y direction? Oh, this one. Should I use the what 4.9 or 16? 16, right? Because everything here is in feet. So what's y final? 10 feet, right? What's y initial? 6.5. V initial y. That's going to be my V initial sine 28, right? T we don't know. So do we have the correct number of equations and the correct number of unknowns to solve this? How many unknowns do we have? Two unknowns, and the same two unknowns appear here. Yeah, somehow we can combine these two equations and solve for our variable that we want. What's the easiest way to solve this? I think probably the easiest one to do is go like this. Substitute it into here because there's only one place to substitute it into, right? Just that, and then you get rid of it. So that 10 minus 6.5 . So I substitute that for V initial, right? Then I have sine 28 t minus 16t squared. Actually, that becomes really easy now, right? V initial is 15 over cosine 28t. Which one? The initial height?
Oh, no, I get it now because it's
6 feet 6 inches. Yeah, half. Yeah. Yeah. So now that's 3.5. Okay. So now the t and the t cancel, which is what I love because then it's not a quadratic, right? Then you have here 3.5, 15 tangent of 28. So you solve for the time that it takes for the ball to get there, right? So 16t squared . Huh? T is equal to 0.52 seconds. Now take that time and put it into here because the shooter is not interested as much in the time. He wants to know how fast should I throw it at, you know. And then you put it into here and solve for V initial. I think that was the best, quickest way. Solve for V initial, plug it here, solve for T, very quick, put it back, get the V initial.
32 with 12.
Okay, now if the player says feet per second, I don't know what does that mean. Most players don't know that. They convert to miles per hour so they can know, right? So what do you do? Divide by 5280, right? 5280 feet is 1 mile, and then 3600 seconds is 1 hour. So divide by 5280, multiply by 3600. 21 miles per hour. And then you and him can start practicing on shooting. Then you do the speed thing, the radar gun, right? And you say, no, you're throwing too fast, too slow, too fast. Then you get the muscle memory, you know. Free throw shooting is all about just patience, not listening to the crowd, you know, not getting the pressure. It's not that easy. It's one of LeBron's Achilles heels, right? What do you call it? Achilles heel. Is that what they said? Yeah.
He's not good.
Not as good as he should be. It's like 73, 74%. Jordan was like more like 88 or 90. Nash, those guys, 90 in the 90s. That 10% difference is a huge. You know, it makes a difference between a game. Of course, there's so many complications. Maybe you're shooting to the right slightly. Maybe you're shooting to the left slightly. Maybe your angle's too low. Maybe your velocity's too low. Okay, how about, let's call that part A. So part B. If the player runs up the court, let's say he's running at 1 So now instead of a free throw, you're actually running, and then you do a floater, right? So you keep running, and then from that location, right, you're running, and then somewhere about here you're running, and then you do the floater. So let's assume you do it at the same speed, 32, but you can't keep the same angle, right? Because you're running. So should you do it lower angle or higher angle? Yeah?
Higher.
Why?
Going faster, so it should get your just a longer attention.
Yeah, it should take a longer time to get. Huh?
Your shot's not gonna be being arced, so it falls in, right?
Yeah, I mean you kind of know it by doing it if you played, you know, but maybe you can't really explain it in words. Who's a player here? Right? Yeah, because you have a horizontal velocity, right?
Yeah.
Which tends to make it go that way quicker. So if you do a shorter angle, it's going to tend to go even more straight, right? So you probably have to do it a higher angle. So you probably have to do 32, 34. So how do we build that into the physics, into the equations? What changes?
You add 20 to be at x, you add your range.
You add 20 to the initial velocity?
The x.
Only x direction, because you're running mainly in the x, right? Yeah. Now if you jump while you run, then you add the y direction. Yeah, that's right. So, but if you're running mostly straight, then you shoot, then you add the 20 mostly to the x direction. You see? So then what changes? What happens here? Oh, so then now what I have to do is calculate v initial x is going to be what? What do I do? 32.12 cosine of theta, because I don't really know what the angle is, right? Hold on. I'm shooting at 32, but I don't know the angle that I'm shooting at. Then I'm adding to that what? 40. You see?
I mean, the speed you have to throw at like 3.
Oh no, I'm saying the speed is 32.
What is it? 20? Is that he's read 22?
No, he's running at a speed of 20.
So is the 32 like the speed of the ball?
Yeah. So the speed of the ball, with respect to him, is shooting at 32. But with respect to the ground, he's running at 20. But only in the x direction. You see? So what's the velocity of initial of the ball with respect to the x? 32.12 cosine of whatever angle he shoots at plus 20. Now should I go like this? 32.12 plus 20 parentheses cosine theta? Or is it the cosine theta only times this? Yeah, you see, if you add the 20 to this, then that means he's shooting at 52.12, right? But that's not what he's doing. He's shooting at 32, but running this way at 20. This is kind of like the plane wind problem almost. Like this is like the wind speed. This is like the almost like the plane speed, you know. So now you're gonna do 32.12 cosine 20, theta plus 20. Now the initial y is what? 32.12 sine theta, but there's no 20 added to that because it's not running in the y direction. Okay, now what changes about the equation? Well, this is still 15, right? In the x direction. So 15 v initial xt. So what's v initial x? And then what's the y direction? In the y equation, you have 10 equals 6.5 plus v initial sine theta. Well, actually, it's going to be this guy, the initial y. So 32.12 sine theta t minus 16t squared. So there's my two equations and two unknowns. But now the unknowns are the theta and the t, and the theta and this t, but the velocity I do know. Okay, so now what's the best way to solve it?
Substitute time?
Probably time is the best one because you can't substitute cosine theta. Right? Maybe substitute time. Well, how about if we do it this way? I have an idea that might work. 15 over t minus 15 over t equals 3212 cosine theta plus 20. Right? Then you subtract 20. Right? Then you have here 3.5 plus 16t squared over t is equal to what? This goes over here, plus 16t squared over t is equal to 32.12 sine theta. Right? Then what do you do?
Divide.
Square, 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 square. Huh? Does that work? Now why'd you square it, Mr. K? Because sine squared theta plus cosine squared theta is 1. Right?
So you have, yeah.
It's an evil laugh. Right? So that gives 3.5 plus 16t squared over t, quantity squared, plus 15 over t minus 20 quantity squared is equal to 32.12 squared cosine squared theta plus sine squared theta, which is 1. Proud of yourself, huh? All right. Now put this in solver on your calculator and have it give you the variable t. Okay? Solve quantity 3.5 plus t is 0.2928 seconds. Right? So just put that in the solver and have it solve that. Now let's see if the answer that we get makes sense. Put that into what equation? Just put that into here and solve for theta, right? Into one, either one of the equations. So 15 is equal to, so put the t, I'm going to put the t into this. Right? Well, then just calculate 15 divided by this minus 20, right? Now I get 0.972276 equals cosine theta. Is that right? Doesn't sound right. And the inverse cosine of that? $13.5 degrees. So he has to shoot more straight. Huh? You see? You show this to the players and they go, my God, we've been arching it more if we run. You say, no, you're doing it wrong. You got to do it more straight if you run. Everybody did it wrong, including me. Everybody said it wrong. See, they left early, so their basketball game is gonna stay.
Oh,
You gotta shoot more straight if you run.
Yeah, because time is shorter actually. So if you were to, if you were to go it, then if you shoot it too high, the T is like larger. So Vx times T, you would definitely go over the board, right?
It goes over the board.
Yeah. Because T is larger. If you shoot it like
Let me get my phone and try it.
no,
Shoot the phone, and right. Let's say you do it with the eraser, you know. No, don't want to remove the eraser.
you can use this. Yeah.
Oh yeah, here's my basketball. Okay.
Okay.
So now if I run to hit the same spot,
Yeah,
I have to do a lower angle.
lower. Yeah. If it is higher,
Who was saying higher?
it's gonna go.
They were all like proud of themselves, like we
Science
played
proves
for
that.
years.
It's funny.
thought it was
I saw this documentary about snipers, and none of